We're at a point where we've defined a lot of important set operations, so we can actually start doing some things with those. In this video, I'm going to go over a proposition from the first chapter of the book that I've referenced previously, Abstract Algebra Theory and Applications by Thomas Judson. Let us begin. Let A, B, and C be sets. Then, A union A is A intersect A equals A minus A is the empty set. 2, A union the empty set is A intersect the empty set is the empty set. 3, A union B union C, where we do B union C first, is the same as A union B union C. And A intersect B intersect C, where you do the B intersect C first, is the same as A intersect B intersect C. And there are 3 more properties that I'm going to write down, but I'm not going to read them off right now because this is just a lot of information. These are the 6 statements within this proposition, and let's just start tackling them one by one because as we go through them, they will make a lot more sense. I'm not going to do straight up proofs for all of these. I'm just going to explain why some of these things are true, and maybe through examples, maybe through just the overview of an argument. These sorts of propositions are great when you're trying to solve problems or whatever, because you can just come back to the proposition and reference what they have in it, and then just see if any of the properties help you with the problem you're trying to solve or something else that you're trying to prove. The first statement is relatively straightforward. It's okay if it's not straightforward because you're new at this, but it's relatively straightforward. If you sit down and think about it, it will start to make a lot of sense. A union A equals A because the union takes everything from both sets and pushes them into one set. But if we're just unioning A with itself, we're not adding anything. The union isn't contributing anything else to the set. So we're still just left with A. Also, A intersect A equals A. This is because the intersection is taking every element that's in common between the 2 sets, which is just going to be all of A again. And then A minus A. So if you remember, the subtraction operation for sets is that you take the set on the left-hand side and remove from it everything from the set on the right-hand side. So we're going to take A and remove all of the elements from A from this set, which leaves us with nothing. Next, A union the empty set is equal to A. This is because, again, the union, we take everything from both sets and put them into one set, but the empty set's not going to contribute anything new to this union, so it just remains A. And A intersect the empty set. The intersection takes everything that both sets have in common, but since the empty set doesn't have anything in it, they have no elements in common. Number 3, A union B union C equals A union B union C. With something like this, and I'm just going to actually explain this for the union. There's this property here for the intersection as well, but the same concepts of how I explain number 3 for union will apply to number 3 for the intersection. If we look at the union case, A union B union C, this is simply saying it doesn't matter if we evaluate B union C first and then union it with A, or if we evaluate A union B first and then union it with C. And this works for union and intersection, but not with mixed operations, not if you have union and intersection mixed. And let us just go ahead and 3 relatively simple sets. If we were to do A union B union C with the B union C in parentheses, that means we evaluate B union C first. So we have A union, and then B union C ends up being 3 through 9. Then A union 3 through 9, well, A can add some elements to this. A has 1 and 2, which is not already in 3 through 9. This becomes 1 through 9. An example is not a proof, but it is showing you how this is working. A union B union C. This one means we do the union of A and B first. So A union B gives us 1 through 7, and then we do the union with C. And then if we union this with C, C, in addition to containing numbers in this set already, has 8 and 9. This will go 1 through 9. And we get the same result here and here. The point of this is that when you have a string of unions, it does not matter which ones you evaluate first. You can do it in any order, and it's going to be the same result. And this actually applies really for any strings of unions. I could have something like this, and it would be the same as A union, maybe I would say B union C, union D, union E, union F. right? I can put parentheses anywhere in this union and evaluate the union of any two of these sets first, and I'll still get the same result. And it's really important to know that our operations, in this case is all union, but same thing with intersection. As long as our operations are all the same throughout, all union or all intersection, we can do this sort of thing. Once you start mixing the operations, you can no longer necessarily do this. So it is something to be careful of. But when you're just working with one operation, you can just look through it, and whatever you see fit as doing first to make your life easier, go for it. Next up, we have number 4, and we've discussed this a lot and have done it in the other examples. A union B equals B union A, and same thing for intersection. All this means is that we can flip the order that we intersect two sets. It doesn't matter because A union B is just saying take all the elements from A and B and smush them together into one set. And it doesn't matter if we express that as A union B or B union A, it still has the same meaning. Similarly with intersection, it just means take the elements that are in common with these sets. So it doesn't matter if we put the A first or the B first when we're expressing that we want to get the common elements from A and B. Numbers 5 and 6 are a bit trickier because we start to mix the operations of intersection and union, and then things aren't as straightforward and they require a bit more thought. So this first one, or number 5, says A union B intersects C, is the same thing as A union B intersect A union C. There's a lot that I can say about this to explain it, so I'm going to try a couple of different explanations, and you can pick what jives with you. One is to think about it as the distributive property. Think of something like, you know how we in algebra did stuff like 5 times x plus x squared. And that's the same as 5x plus 5x squared. When I see this sort of property with the unions and intersections, I think of the distributive property because it mirrors that. So this is in no way a proof or a verification that this is true. It's just a way to help you remember this property. This is very similar to this algebraic distributive property where we start with the union basically is corresponding with the times and the intersection is corresponding with the plus, and we take the A union through to both elements. So maybe that will help you with remembering this property when you want to apply it. To help with the actual visualization of what's going on here, I'm going to draw a Venn diagram. And unfortunately, Kamala Harris has ruined Venn diagrams for me because I always just want to say, you know, the things with the 3 circles?
Venn diagrams, those 3 circles, right? And then let's just see where they overlap.
You will not be surprised because I have constructed a Venn diagram on this. Remember those 3 circles, how they overlap?
I love Venn diagrams, so I just do.
That aside, let us draw these 3 circles. We'll maybe have A, B, and C in this order. I am absolutely terrible at drawing circles. Here we want to do A union B intersect C. B intersect C is going to be this stuff right here that falls in common between the 2 sets. And then if we union this with A, we end up adding all of A. So if we look at this from a Venn diagram point of view, this shaded area represents A union B intersect. Now let's do a Venn diagram for this half. Here, since we have parentheses, the first things that we do is we do the operations within the parentheses. So I'm actually going to use a light color for this one. A union B is going to be all of the stuff in A and B. This is what A union B looks like. And A union C is going to be everything from A and everything from C. A union C is this green shaded area. Now we have in yellow A union B, we have in green A union C, and then we are intersecting those 2 sets. So when we do the intersection, we're going to find all of the parts of this Venn diagram that are shaded in both yellow and green. So we can see that's all of A is shaded with yellow and green both. And this piece right here is also shaded with yellow and green. What we have is A union B intersect A union C is this area that's shaded in blue, and you can see that it corresponds exactly to the original Venn diagram, or the Venn diagram drawn for A union B intersect C. So Venn diagrams are a great way sometimes to visualize these set operations, and there is zero shame in drawing out Venn diagrams when you need to, because these things get complicated and or your brain has trouble just keeping track of everything that's going on. So even though I've done this sort of thing a bajillion times, I'll still write stuff like this out in a Venn diagram if I need to, because maybe I'm holding too many things in my head, or I just want to have a visualization that I can refer back to later, or to just check my work. Nothing wrong with writing out Venn diagrams, even though it seems a little infantile, maybe if you remember doing these in like elementary school, but it's a great way to organize information, and they are a powerful tool. 6 now is A intersect B union C equals A intersect B union A intersect C. I won't write this out next to the distributive property again, but you can see how this very much mirrors the distributive property. I mean, you can look at 5 and 6, seeing them side by side, you can see that they really look very similar, except the unions and intersections are just completely swapped. So what I will do is the whole Venn diagram thing for these. So on the left-hand side, we want to do B union C first, because that is in parentheses. So B union C is everything in B and everything in C. It looks like this. And then what we want to do is we want to intersect this with A. We're going to look at B union C, which is the shaded in area, and we're going to say, okay, what of that shaded in area is also in A, and intersect the two. And that is going to be these 3 regions here. They're in B union C, but they're also in A. So that is what this Venn diagram looks like. Next, we want to do A intersect B, so we'll do that in yellow. And then we want to do A intersect C, so I will do green for A intersect C. Now, we're taking these 2 sets, which are represented by these areas shaded in yellow and in green, and we're going to union them. So when we take the union, we take everything in both of those sets. So you can see when I take the union here, I end up with the same shaded region as I do on the left-hand side over here, showing visually that these sets are the same. And some people would say a Venn diagram proof is a reasonable proof. Others might not, and they would want it written out in words and symbols. So I'm hesitant to straight up call this a proof, but it's at least a visualization that shows you pretty well why these 2 sets end up being equal. And it brings you through the process of actually constructing the result of this expression, which is also very helpful because it helps you see how you arrive at that.
So I run through the maze, and then I find there's some guy named Queez.
Queez, boring man.
Gremlin T. Squeerfish.
Minus opposite.
Janitor Snoutlick.
Dirt stick. Nothing else.